Warning, the video you're about to watch contains mathematics at the level of integral calculus, also known as Calc 2. All material has an assumed prerequisite of differential calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video I am creating because of something that happened in my integral calculus class today, where I decided to kind of reveal a part of my thought process to my students about how I view functions and integrals and derivatives in calculus. And it ended up being so impactful, at least I believe it was, so much so that I wanted to dedicate a single video to just this idea and to talk about why viewing calculus this way can be very, very helpful. So to understand what I mean by the ladder view of calculus, I just drew out a ladder, go figure. And the most important part of this ladder is the rung that you're standing on. And this rung, let's just pretend, is the function f. Well, when you take the derivative, and I'll start with derivatives because people can watch this while they're in Calc 1 or Calc 2. So if you're in Calc 1, then the derivative conversation is kind of important. If you take the derivative of a function, it's kind of useful to think about it as going down a rung on that ladder. At least I think it is. It may not seem that way to you, but it is kind of how I feel about it. So if you take a derivative, you go down a rung and you get f prime. Let's say you take two derivatives, go down two rungs, then you have f double prime. If you take an antiderivative, now I'm going to the end of Calc 2 or Calc 1 and into the beginnings of Calc 2. If you take the antiderivative of f, well, you get the integral of f dx. Notice I didn't bother with the f of x. I apologize if you're a stickler about that, but I just write f, integral of f dx. That is a step up on that ladder. And by the way, some people will call that capital F because that is traditionally the letter used for the antiderivative of a function. But let's just for now not assign it that. If you want to go up two rungs from your blue rung f there, you would need to take two antiderivatives. Visually, it goes like this. You take the integral of f of x dx, and again, dx. Actually, let me make that a little more apparent. I'm going to step back a little bit. It's the integral of something with respect to x. The thing that you're taking the integral of with respect to x is the integral of f of x dx. There you go. I put in the f of x for you. So anyhow, two steps up would be two integrals up. One step down would be the derivative of f. Two steps down would be two derivatives, and so on and so forth. Now, part of this conversation that's critical to understand is that when you differentiate a function, you can lose information. So I'm going to write that off to the right-hand side. There we go. Differentiating can cause a loss of information. Now, what do I mean by a loss of information? And you know what I'm going to do just to give myself some room for handwriting purposes? I'm going to grab that picture and move it over. Beautiful part of having a digital whiteboard. So what do I mean by losing information? Well, something I tell my Calc 1 students quite often is that if f had a domain of, let's just say, I'm going to put a little column here for domain. So domain. Let's pretend f had an original domain of negative infinity to infinity. Let's just pretend. Well, when you take the derivative, you could lose part of your domain. So your domain might be, I'm not saying it's exactly this, I'm just saying it could be like negative infinity to 1 union 1 to infinity. In other words, you took a derivative and you lost the element x equals 1 from your domain. If you take another derivative, you just might lose even more from your domain, or you might keep the current domain you have. So it is not that you will, It's that you can lose information when you take derivatives. And I think I'm going to rope this up as well and just move it over to the right because I just thought of a second column I want to put on here. And for this conversation, I think it's going to be worthwhile for me to maybe reset that and just pretend for a moment that our original function, just again, pretend, had a domain of, I don't know, let's say -3 to +5, including +5. Okay, let's say we take the derivative of our function, and it could be that the derivative keeps the same domain. That's fine. But then if you took one more derivative, it might end up losing a center out of that domain, or it could lose an edge out of that domain. There you go. So that's something to note, that you could lose a center or an edge. I'm going to actually call it a center for now. Although it could have lost the edge. Who knows? It could actually lose both in a single step. So when you take derivatives, just be aware, domains, you could lose pieces of your domain. You're like peeling away the domain when you take derivatives. You're losing quality. On the other hand, when you climb this ladder and you integrate, you can possibly gain information. And again, that word can is very important. It's not that you're definitely going to gain information, it's that you can gain information when you climb this ladder. And so, for an example, what we have here, we have this integral, we have this function that has a domain of -3, not including, all the way up to 5, including 5. Well, when you integrate, you might gain the edge on that domain. That could very well happen. Now, with domains, once you have both edges included, well, any sort of integration after that, so as you climb this ladder, you're not going to gain anything else because you filled in the entire interval basically. But the idea is still there, that as you climb the ladder, you can gain little bits on your interval, which is called your domain. As you go down the ladder with differentiation, you could possibly start shedding parts of your domain. And if you take more derivatives, it could be that you end up with an infinite number of holes in your domain. That'd be a weird function, but let's just pretend we're along for that ride. Now, if you're in Calc 2 and you're in sequences and series, specifically power series and intervals of convergence, by the way, if you're in Calc 1, you're done with this conversation now. But if you want to stick around, I highly recommend it. There is some interesting information here. So if you think about intervals of convergence, your original function could have an interval of convergence. Your original power series could have an interval of convergence. Let's just pretend that it's, I don't know. Let's just create something kind of cool. Like, let's say that your original function had an interval of convergence of, actually it could be kind of the same, but I'm just going to go -3/7 to 15/7, not including the 15/7. So that could be the interval of convergence for some original function you're working with. Well, when you take an integral of that, again, you could possibly gain an edge on that or not. So it's not that it has to, you have to check the edge points, but it could be the case that you gain the edge. If you take two integrals, you might, again, gain the edge you didn't gain before. So that is a very realistic possibility. When you differentiate, you might lose an edge. And I'm not color coding this, which is unfortunate, but oh well, what are you going to do? So in this case, let's just pretend you take the derivative of your power series and you check the edges and you find out, whoa, after that first derivative, I lost that edge at -3/7. Well, such is life when you take a derivative. Now, just a heads up with intervals of convergence, you're not going to lose the center. So the worst case scenario is you've lost convergence at both edges, but nothing else is going to happen. So with intervals of convergence, you're not going to get holes in your interval of convergence. Instead, you'll just lose the edges when you differentiate, possibly, or you'll possibly gain edges when you integrate. So this is my ladder view of calculus. Some other ways you might want to think about this. The fact that you have an original piece of work right here, and when you take copies of it, derivatives of it. That's what really I'm thinking of when I say copies. Every time, let's say you take a photocopy of something, you lose a little bit of quality. Each time you lose information when you take a derivative. If you go back a step to try to repair and get back to the picture prior or whatever it may be, you'll gain information. And that's the idea. So nothing beats the original unless you have an original prior to that original, where you can gain a little extra information. If you think about compression in JPEG images, so every time that you edit a JPEG, which is an image, it slightly compresses that image. You actually lose a little bit of information every time you work on it. You lose a little bit. On the other hand, if you can somehow recreate the image prior, you'll get back some information, right? It's harder to get back information, just like it's harder to integrate. It's harder to get back information into its original form. So there's a lot of analogies with real life applications. Think about, well, I don't know if anybody's old enough who's listening to this, but think about if you had a cassette tape. Probably nobody watching this knows what that is, but if you have a cassette tape and you make a copy, you could totally hear the difference in the copy. It's a lot worse than the original. So you lose a lot of information every single time that you make these derivative works. All right, that latter view of calculus is going to be incredibly helpful for another video I'm doing, which is all about how to recreate power series given a function and the kind of choices you're going to make. So I just wanted to use this as a springboard into that conversation. I hope it was somewhat interesting and helpful for you. Have a great day.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.